Welcome to this morning's session. The first speaker is Professor Yao from Tsinghua University. Actually, there's no introduction needed for Yao. He is one of the founders of the field of geometric analysis, and he has proved many resolved to many conjectures and proved many theorems. And now he also collects many honors and prizes, of course, including the Fields Medal. So today he is going to tell us the canonical connections on holomorphic vector bundles and their applications. Professor Yao, you may start.
Thank you. I'm honored to be invited to come to give this talk in University of Toronto. I've not been in Toronto for quite a long time, but I'm glad that my co-worker, Tristan Collins, is now working in Toronto. And my younger friend, Fred Tong, is also coming to Toronto. So many of these works here that I'm talking are working with Tristan Collins. So his name is here together. So I should say, starting from scratch, a complex manifold, as you know, is covered with special coordinate charts whose transformations are holomorphic. And holomorphic vector bundle is a complex vector bundle of rank R whose screwing maps are holomorphic, mapping into GLRC. This set of coordinate screwing maps up to equivalence defines integrable complex structures. It is a very deep question to find out which manifolds and which complex vector bundle admit integrable complex structure. And if they admit such structure, how do we classify them? For complex structure over manifold, the imaginary number defines an automorphism J on a complexified tangent bundle with the property J squared equal to minus identity. And such a endomorphism is called an almost complex structure of the manifold. Almost complex is misspelling here. The existence of an almost complex structure can be reduced to computation of characteristic classes, Stewart-Whitney classes, and Chern classes, and all that. So it becomes a trackable problem by doing computation on homotopy classes, characteristic classes. But it's a deep question to know which almost complex structure comes from integrable complex structure. I make a conjecture in the late 1970s that any almost complex manifold with dimensions strictly bigger than 4, bigger than equal to 4, real dimension bigger than 4, almost complex manifold with complex dimension bigger than equal to 3, always admit an integrable structure, integrable complex structure. This is a very ambitious question, actually, but I actually try very hard to give a counterexample, and I did not succeed. This would be fantastic if it's true. I believe it's not too far from being true. Suppose we know which manifold is a complex manifold, integrable complex manifold, then it's very important question is which complex bundle admitting an integrable complex structure. This gives restriction on the Chern classes of the complex vector bundle, since the Chern classes must be KK type dependent forms. So there's a natural obstruction. So if the first question that I mentioned about is positive, namely an almost complex structure admits an integrable complex structure, then this problem can actually have some interesting approach to solve it. Namely, the projectified tangent space, projectified vector bundle would admit an integrable complex structure, and this problem can be reduced to study the characteristic classes, and would be interesting to figure this one out in more detail. Anyway, if we simply want to know whether the vector bundle has a integrable complex structure, if we write in terms of curvature and connection of the bundle, then it's well known that the vanishing of the two seal part of the curvature is the condition for the bundle to admit integrable complex structure. Well, this is a very important problem because this will tell you a great deal about the Hodge conjecture. If we can make a vector bundle to be holomorphic, because by the theorem of Chern, that every holomorphic vector bundle whose the Chern classes would be representable by algebraic cycle. Now, in order to understand much further, I'd like to do an important task, is to build a canonical geometric structure based on the complex structure that we just mentioned. Well, canonical would mean it's unique up to some natural equivalence relationship. And if it's not unique, it should be parameterized by some finite dimensional varieties, which we call moduli space. And any nice moduli space should be Hausdorff. This condition gives reasonable condition on the canonical structure. So basically, we want to give a canonical structure on the bundle or on the manifold, and we use them to define the moduli space in a suitable manner. We would like to see that the moduli space is Hausdorff. This turns out to be compatible with the geometric invariant theory pioneered by Mumford. Mumford introduced the important concept of stability in algebraic geometry. I learned of this kind of stability very early in 1971 when I just graduated from Berkeley. Met my friend David Giesinger in IAS, where we were members. And we talked a lot during dinner time. And David told me the geometric invariant theory developed by Mumford to construct moduli space of algebraic surfaces of general type. That's what he tried at that point. He succeeded to do it. Mumford actually already tested out for algebraic curves, where he wrote a fundamental paper with Pierre Deligne, which is now called Deligne-Mumford compactification of algebraic curves, moduli space of algebraic curves. So David also construct moduli space of vector bundles over algebraic surfaces. So I think these are very good work using stability, geometric invariant theory by Mumford. Although at that time, Philip Griffiths actually told us when I was at Stanford that it is not the right direction. But in that case, the concept of stability was extensively used in this construction of moduli space. I'm convinced that algebraic stability should play an important role if I want to use differential geometric means to construct moduli space. So basically, I want to give each object some canonical connection or canonical metric, and then I use this canonical metric to construct a moduli space to make it to be Hausdorff. So we have the same goal, and I therefore think that stability, algebraic stability, should be very much linked to canonical metrics or canonical connections. Well, so the first important step that I thought was to use the very well-known canonical hyperbolic metric on Riemann surfaces due to Poincaré and many people to high-dimensional algebraic manifolds. And this has been the K-Einstein metric. The Wade-Peterson metric coming from the K-Einstein metric becomes an important means to construct metrics on a moduli space. so that the resulting space is Hausdorff. So that's why we think that the existence of high-dimensional canonical metric is related to the concept of the stability of the algebraic object where the canonical metric resides. So existence of Kähler answer metric is therefore expected to relate to stability that I thought a long time ago, 50 years ago. So beginning with my time as a graduate student, I firmly believe that the fundamental way to understand geometry is to build interesting canonical geometric structure from scratch. That means given a manifold, suppose we are given as little data as possible, I want to construct some geometric structure out of it. So here we are talking about if you have holomorphic structures, we want to construct something over this holomorphic structure. So most of the structure that I'm interested in are defined by nonlinear equations, mostly nonlinear elliptic equations. So many years ago, I formulated the following principle. For any nonlinear elliptic system in geometric analysis that is invariant under non-compact continuous group action, the group action could be infinite dimensional group action, existence of a solution to these equations is equivalent to a stability problem related to a non-compact group action on certain finite dimensional manifold. So in some cases, this is what we see. The moment map actually was studied quite a lot by Simon Donaldson later. So this is the basic philosophy behind it. The first major task was to find conditions for the existence of Kähler metrics. And Calabi, of course, made the first fundamental progress in 1954, but he did not realize the importance of algebraic stability to the existence of Kähler metric on algebraic manifolds. This was conjectured by me in the late 1970s. Well, when I proved the Calabi conjecture in 1976, and also proved the existence of Kähler manifolds for those manifolds with negative Chern classes, which was independently proved by Aubin, I proved the Chern number inequality for such manifolds, namely the second Chern class and the first Chern class squared has some inequality between them. This was a rather well-known important question in those days, and it was solved by me and also by Mioka and using the method of Bogomolov at that time. We proved the same inequality for algebraic surfaces. I thought this was a very natural inequality coming from differential geometry of Kähler metric. So I was taken by surprise, actually. They can be done by algebraic method purely. And their method was based on stability. And so therefore, I was pretty firm to believe that existence of Kähler metric is also related to stability. Because using different method, we arrive in the same conclusion. Then, after the construction of Kähler metric on manifolds, a natural generalization was to look at holomorphic bundles. One wants to construct Hermitian connection on the bundle so that the trace of the curvature is either zero or a scalar multiple of the identity acting on the bundle. This is a natural generalization of instanton bundle in real full four-dimensional manifold. This is called Hermitian-Young-Mills connection in high dimension. In real four dimension, it can be written in terms of anti-shelf connections. Well, observe that this condition implies the bundle is actually slope stable in the sense of manifold. Many people then immediately, including myself, realized that the converse should be true. At that point, I already constructed the rigid flat Kähler metric on the KP surface on the tangent bundle of that manifold based on the Calabi conjecture. This metric gives rise to the Hermitian-Young-Mills connection. When I visited England in 1981, my friend Hitchen told me that his student Simon Donaldson just proved the existence of Hermitian-Young-Mills connection on holomorphic bundles on KP surface that can be deformed to each tangent bundle. So these observations certainly support the conjecture on Hermitian-Young-Mills connection on stable bundles. So although it's just the beginning of his thesis, it already gives a very strong indication what should be true. So Ken Ruenberg and I was actually working on this problem already, but we need to overcome some question of regularity for the construction that we use. In the meantime, when we are working on it, Simon Donaldson used a parabolic geometric flow, which comes from the idea of rigid flow for bundles. At that point, Hamilton just solved the rigid flow for manifold with positive rigid curvature. So Simon immediately adapted a similar method for algebraic surfaces. And he succeeded to prove the conjecture for Kähler manifold, for algebraic manifold of 2 dimensions, algebraic surfaces. Shortly afterwards, Ken Ruenberg and I were able to accomplish our task for bundles over Kähler manifolds, that it is equivalent to stability, slope stability, for the existence of Hermitian-Young-Mills connection. This is a very important theorem, and which later Jun Lee and I generalized to basically arbitrarily complex manifold with a so-called Cartesian metric. So then Simon Donaldson was able to handle the high dimensional problem for general algebraic manifolds by reducing it to algebraic surfaces. But his method can only work for algebraic manifolds because he need to use hyperplane sections. The application of the work that I did, Ruenberg, actually go beyond Kähler manifolds. So it's important to know the theorem also holds for non-Kähler manifolds. So therefore, there's a complete and satisfactory existence theory for the Hermitian-Young-Mills equation, which give a correspondency between algebraic geometric stability and the stability of nonlinear PDE. So the statement says the following thing. Given a compact Kähler manifold and E is a irreducible holomorphic vector bundle, then E admits the Young-Mills connection if and only if for every torsion-free coherent subsieve, we have this inequality, which is called Mumford stability. This theorem has many applications and extensions, which I mentioned, especially extension to Higgs bundle. Higgs bundle is very similar to this thing, except we have an endomorphism to help an algebraic condition. But one needs to use this analytic tool that Ken Ruenberg and I developed. This was done by Carl Simpson in his thesis in Harvard in 1987, I think. So the Higgs bundle concept was introduced by Hitchen, and Carl Simpson was able to understand it for high-dimensional manifolds and becomes extremely useful. But analytic side needs the argument that Ruenberg and I use. The reason that it was used is to characterize the equality case of the Bogomolov-Kiesinger inequality. There's an inequality for the train classes. When the equality holds, there's a rigid phenomena, which implies the bundle is projective flat. This projective flatness is tremendous importance for the application of Carl Simpson to apply Higgs bundle to study deformation of mixed Hodge structure. Well, it's actually quite interesting to ask whether we can generalize the Donaldson-Wurmberg-Yau theorem to the setting of anti-shelf-due connection on 4 manifolds, which is not necessarily holomorphic. Would be very nice to understand a necessary and sufficient topological condition for the existence of an anti-shelf-due connection on a vector bundle over a compact 4 manifold. So the idea of Hermitian mules can be considered a generalization of anti-shelf-due connection, but the theory that it develops should have some analog in the original topological question on compact 4 manifold. The existence of a good connection would imply inequality of characteristic numbers of the bundle, and rigidity would lead to flat bundles and therefore projective representation of the fundamental group. So it should give you some hints about how to give representations of the fundamental group of 4 manifolds. Well, the existence of such anti-shelf-due connection has not been done. It would be nice to do it. Now, in this regard, Taus has proved some important results about existence of Riemannian matrix with anti-shelf-due curvature on a 4 manifold after connect sum with a large number of CP2s. So he has to stabilize the situation by taking connect sum with CP2s. This for arbitrarily smooth manifold. I believe there's a suitable notion of topological stability that characterizes the existence of such metric without taking connect sum with arbitrarily large number of CP2s. And it would be nice to understand such a condition. Well, beginning in the mid-1960s, 1980s, string theory becomes an important part of string theory and all that. And Calabi-Yau metric has been useful, and so is Hermitian-Young-Mills connection in understanding meter symmetry, D-planes, and all these important questions in mathematical physics. Meter symmetry becomes a mysterious duality between complex geometry, deformation of complex structures, and symplectic geometry. They are supposed to be isomorphic to each other under suitable formulation of that. In 1996, my friend Andy Strominger and my postdoc Saslo at that time, we developed a geometric explanation of meter symmetry using special Lagrangian fibration, special Lagrangian tori. I think this is a rather geometric, beautiful explanation of meter symmetry. So, well, there are supposed quantum correlation and all very complicated things, but without assuming there are quantum correlation, my former student Kongren and Saslo, we then use this SYC proposal to derive a new nonlinear PDE, partial differential equation, for Hermitian bundles, which is supposed to be mirror to special Lagrangian cycles. It turns out generalized the Hermitian-Young-Mills theory of Donaldson-Wurmberg-Yau. These equations describe certain BPS state in type 2A B string theories. So this is the part of the problem that I like to address to. So based on SYC picture of meter symmetry, there's an important concept of special Lagrangian cycle, and we want to study its mirror, and this is what we call LYC equation. So let me explain a little bit more detail. Well, meter symmetry arises from the discovery that type 2B string theory compatible on a Calabi-Yau would be equivalent to type 2A string theory compatible on a different Calabi-Yau, and vice versa. So each of these theory come with a collection of D-planes, which we can think of roughly as the particle that live in that theory. In type 2b string theory, the D-branes are associated with complex geometry, while in type 2a, they are associated with symplectic geometry. Since both theories describe the same physics, the particle must be the same. They provide correspondency between complex geometry on X and symplectic geometry on its mirror X hat. So around the same time, slightly earlier, Kontsevich formulated the mathematical proposal of homological mirror symmetry, which conjecture the mirror symmetry can be explained as the equivalence of two triangular categories. One is the derived category that Kontsevich proposed, and then there's another Fukaya category on X hat. They should be isomorphic. This category describes particles in our physical theory, depending on whether we view it as a type 2b or type 2a. But not all of these particles are really realistic. The realistic particle minimizing a Lagrangian action functional and solve some equation of motion. The expectation is that every particle should decay, essentially uniquely into stable pieces. So in type 2a theory, the stable objects are special Lagrangians. And what is special Lagrangian? It was introduced by Harvey and Lawson quite about maybe 7 or 8 years before this appearance in string theory. And in string theory, it was introduced by Becker, and Strominger, without knowing the work of Harvey and Lawson. So what is that? Well, given Calabi-Yau manifold, you have a holomorphic volume form omega and a scalar form small omega. An n-dimensional view, n-dimensional submanifold L is called special Lagrangian if it's Lagrangian in the sense that scalar form restricted L is equal to 0, and then imaginary of exponential minus I theta hat. Theta hat is a constant times omega restricted L is equal to 0. So this is called calibrate geometry, and such a manifold L is a minimal submanifold, LA minimizing. That's actually one of the reasons why Harvey and Lawson interested in this subject. Anyway, this is a very beautiful geometry behind it. It is a fully nonlinear equation. And Richard Thomas and I was working on this object when SYC conjecture was developed. So in late 1990s, Richard Thomas and I developed some conjectures about stability and existence of special Lagrangians based on mirror symmetry and the DUI theorem that we developed. So we were very interested to understand this Lagrangian cycle. Well, in the type 2b theory, the stable objects are holomorphic vector bundles with Hermitian matrix satisfy certain nonlinear PDE. This PDE was derived by Leung, Yau, Sartre using the SYC mirror symmetry picture. And it becomes a real Fourier-Markov transform to transform the special Lagrangian equation from type 2a. So there's a beautiful Lagrangian equation, special Lagrangian equation I just described to you, which is went back to Harvey and Lawson. We used the SYC to transform it to a new equation. And this equation is an equation on holomorphic vector bundles, which I shall discuss. This equation was independently derived by using completely different argument due to Moreno, Minasin, Moore, and Strominger. Around the same time, Michael Douglas actually introduced a purely algebraic approach to understanding the stable objects in type 2a and type 2b string theory, based on the concept of pi stability, which generalized the concept of slope stability in the Donaldson-Uhlenbeck-Yau theorem. So this was a motivation by Mike Douglas. Then Beachlam built upon these ideas of Mike-Douglas to develop the notion of a Bridgeland stability condition. And this would be very much related to what we are talking about, the new equation that we are dealing with. So we would hope to build link between them. So what is the equation that we developed by Leung, Sasso, and myself? Well, the equation goes in the following way. Let X to be a Calabi-Yau manifold with the Kähler metric omega, and let L to be another holomorphic line bundle. The first trend class is not omega, not necessarily omega. We call them set by the LYC equation if you set equation 1. So imaginary of this form defined in there, exponential I minus I theta hat, omega minus fx to the power n equals 0, the real part is positive. Now notice exponential minus I theta hat is a constant, is a S1 value constant. So at the time, we know this equation, and then only after quite a few years, or about 10 years later, Jacob Adam and he was working in Harvard, and I start to look at this equation in more detailed way. There's a misprint here. It's not Alex Sasso. It was Adam and I. Notice that equation can define on any Kähler manifold. We should address it more generally. Well, first of all, it's not hard to see that if we take the limit omega to T omega, so a large radius limit, so to speak, then 1 becomes the standard Hermitian-Yang-Mills equation that Ullenberg and I studied before. So therefore, it was tempting for us to look at this equation as a full generalization of Hermitian-Yang-Mills equation. And this was very fruitful. Now, in fact, we may not need a line bundle to define the whole thing. We just need its first trend class. So instead we call it alpha. Alpha need not be an integral class now. It's just a one-one class, a form, a one-one form. Then we can define this integral, the complex number, which is obtained by omega plus square root minus 1 alpha to the power n, integrate over the complex manifold itself. This is independent choice of representations for either classes. We just depend on cohomology class of omega and alpha. So this is a topological number which we can compare. If we assume that this topological number is not equal to 0, sometimes it's called a charge, and we define the S1 value constant by using equation 3. Then we say that omega and alpha satisfy LYC equation if number 4 holds, where theta hat is defined by this number. So originally, theta hat was just say that there exists such a constant. The constant actually can be computed by using equation 3. But notice that theta hat is actually only defined up to 2 pi. So we need to look at it more carefully. And it turns out if we know equation 4 holds, theta hat is actually defined everywhere. So let's show it to you. Suppose the one-one class alpha is written in the following form. The original alpha plus I dd bar phi. Then we can define a function in the following way. Namely, let lambda 1 up to lambda n be the eigenvalue of alpha omega inverse. And we define the phase operator to be this number as in number 5. So we take summation arctangent lambda j, where lambda j are the eigenvalues of the endomorphism defined by alpha omega inverse. Well, the original constant that we defined here in theta hat was only defined up to 2 pi. But on that hand, if we can solve the LYC equation, namely, if we can solve equation 4, then it turns out this theta hat must be equal to number 5. And this tells you that if we can solve the LYC equation, the theta hat is actually has a leap. The phase operator is defined through arctangent naturally leads to R and gives a well-defined leap of theta hat. Such a leap could be called a branch of the equation. There are two phase conditions which we have been interested in doing. Namely, when the leap phase lies in n-2 pi over 2 to n pi over 2 on the right-hand side of the thing. And then we call such a class to be supercritical phase. In this case, turns out the level set of capital theta is convex. When the leap phase, theta hat lives in even closer to n pi over 2, n-1 pi over 2, then we say that alpha has a hypercritical case. In this case, the theta is convex. Well, in the hypercritical case, turns out all the eigenvalues, lambda1 up to lambda n, are positive. And therefore, alpha is in fact a Kähler class. So we are playing this equation, dealing with the LYC equation, making assumption either it is supercritical or is hypercritical. It would be very interesting to go beyond this phase. Well, so Adam Jacob and I about studied this equation about 7 years ago. So we proved that given two classes, fixed class, omega, the Kähler class, and alpha, a solution to the LYC equation is unique up to addition of a constant. This is not hard to prove. Then we define the following quantity. So we take product of 1 plus lambda j squared. Lambda j is the eigenvalue we defined before. And we take the product of it and take square root. And then we integrate it. This functional turns out is bounded below by the charge that we are talking about, absolute value of that charge. And we prove that if a smooth form exists, which minimizing this functional, then the alpha will solve the LYC equation 4, and vice versa. So we turn the LYC equation to be a minimizing problem. And the minimum value of the functional is in fact strictly positive. Well, it's still a question of how to solve the LYC equation. So the first observation is that we can actually solve it in some cases. We observe that if a Kähler manifold has non-negative orthogonal bisectional curvature, basically the curvature in the alpha bar and beta bar direction, where alpha not equal to beta, we require it to be positive, then we can solve the equation of the LYC, the H11 class, when it is hypercritical. So this class of manifold exists, but not huge. It's still interesting to classify this class of manifold. So of course, compact homogeneous Kähler manifold satisfy this equation. Well, we of course would like to remove the condition on the curvature about non-negativity of the orthogonal bisectional curvature. Then Tristan Collins come in to Harvard. So we were together in around 2019. We proved together the following statement that on a compact Kähler manifold in a supercritical case, so theta hat belongs to this element, this interval with the leaf angle. Then we prove that if alpha admits a representative chi, so that this inequality H holds where mu I are the eigenvalues. And we assume also number 9, then we prove that alpha will emit a smooth solution to the LYC equation. So we find an analytic condition for the existence of the equation. And this, of course, is not most satisfactory, but is interesting as a first major step. The condition is actually, this condition number 8 is actually equivalent to something called a subsolution of the condition. So just like in the case of solving harmonic equations, we want to prove existence of subsolution and then move on to prove that it actually exists. Now, this is natural because it's a necessary and sufficient condition. But there's number 9 we would like to remove. This turns out can be removed that in dimension 3 and dimension 4 by several authors, as we indicate here. And we then prove another important observation. This observation is, I think, is very important. We prove that if the LYC solution exists, and if V is any analytic subvariety of pure dimension P, then we have this inequality, which depends only on omega and alpha. So what does this mean? If for some reason we know how to prove the LYC equation exists, then we prove a rather remarkable trend number inequality, namely number 10, which is true for arbitrary subvarieties. This kind of inequality was not seen before in algebraic geometry, and I think this is rather rewarding to see. Now, there are many ways to prove LYC equation can exist in many important cases, but in any case, we know that LYC implies number 10. Well, as I said, analytic understanding of the equation is important, but the goal is not reduce it to analytic condition. We want to reduce it to algebraic geometric condition of stability. So this was introduced by Collins and Jacob and myself in 2020, and we proved that we conjecture there exists a solution to the LYC equation if and only if 10 holds for all proper irreducible analytic subvarieties of pure dimension P. So in other words, 10, which we observe to be necessary, is supposed to be sufficient for the existence of the equation. And this was conjectured by us, and we solved it in the case of n equal 2. In that case, we actually reduced the freedom to the Calabi conjecture in that case. And because it was reduced to some complex motion pair equation. In that case, we need to use a freedom of Desmaiis and Palm. So we solve this problem, this conjecture for n equal 2, using the work of Desmaiis and Palm and the Calabi conjecture itself. So that was done. And then Gao Chen made a breakthrough on this conjecture 1 year later. He proved that in the supercritical case, there exists a solution if and only if. Yes. Hello?
Maybe you have a few more minutes because time is running out.
Okay. So this will be an inequality that will amount to proving stability. And this is an interesting question. Well, then we want to reduce this kind of stability to more to a similar condition that appear in GIT stable, related to Kemp-Ness theorem. And in 2018, Tristan Collins and I introduced a mirror GIT picture for the LYC equation. Study with this space H that you can see from here. And from here, we look at some GIT stability by looking at the charge. Namely, we define this beta using this thing. And then we found out we define several functional on the this space H that we mentioned. And we prove there exists some geodesics, and where we can restrict the functional over there, and the functional becomes convex. And this functional are constructed out of understanding the LYC equation. This is very interesting because we proved existence C11 solution, and therefore reduce the problem to kind of slope stability. And this has interesting, we are able therefore to reduce the problem or stability to some more algebraic version of it. So we find the obstruction of understand the obstruction solution to LYC equation using some more algebraic information now. These are important, I think, but still needs to be understood much more. So this is related to Beachland stability. We look at filtration of ideal sieve of subvarieties and all that. I don't have time to go through it, but you can see how this whole thing looks like, and this is related to slope stability in algebraic sense, and we can reduce to all this theta by using algebraic means by looking at this path. This path is going to be a very interesting path to look at the stability, and we define the winding angle out of it. And from here, we derive actually quite interesting trend numbers inequality. This is the first time I think we can understand high trend classes involved in those inequality if the LYC's equation exists, and then the high dimension version of it for example, in dimension 4, there turns out to be 2 inequalities, and this was proved later by Han and Jane. And in any case, we formulate this whole thing in terms of more algebraic geometric means later. And I think this whole thing is very interesting. And we have checked how this LYC equation relate to Beachland stability. And we prove that in the case of algebraic surfaces, that LYC implies Beachland stability in many cases, but not conversely. So this raises a very interesting question, how to subtend Beachland stability to be a criteria for LYC existence. And I think there are much more interesting research needs to be done. And this would be very interesting for algebraic geometry, and also for analysis, and also for mathematical physics. And there are curvature flow ways to do it. I don't have time to look into it. So thank you.